Welcome to the introduction chapter of the General Psychology course. In this chapter, we're going to be covering the basics of the history of psychology, as well as some of the fundamentals regarding the methodology of how the behavioral sciences conduct research in the 21st century. To get started with, we'll take a look at the long history of psychology. We're going to take a look as far back in history as we possibly can, instead of looking at the more recent history from the past couple hundred years. This way we can get a broader view of where the principles of psychology have come from, how they've been pulled together and affected society over time, primarily in Western civilization. Now, to look as far back as we possibly can, one of the oldest things that we're going to wind up finding of anything related to psychology is going to be the archaeological evidence for Neolithic tray panning. Neolithic tray panning is a process by which a hole is drilled into the skull of an individual for some medical or spiritual purposes. If you take a look at the television, you can see instances of it. In fact, some of these skulls that have been identified from the archaeological record have essentially showed that after the hole was drilled in the individual's skull, they were alive for some amount of time afterward, a substantial amount of time, not an hour or so. And the evidence for that is, as you even see here, the bone grew back in the skull as time went by. So it didn't appear that these holes were drilled in individuals' heads as murder attempts, but rather as some sort of medical or spiritual process. Now, of course, in Neolithic times, there's no record for why somebody would actually do this. But thousands of years later, the practice was still being done in various places around the world. And as a result, there was documentation about why it was completed. There were two general reasons. One of them was related, at least in Europe, to the idea that evil spirits were in the head of an individual that was behaving oddly, and so a hole was drilled in the skull of the individual to release the evil spirits. In other instances, it seemed to be more related to a medical issue. For example, in South America, during the 1500s, the Spanish documented the role of tray panning as a way for medical doctors to just improve the likelihood that a person would survive a head injury. After tray panning in the Neolithic period, medical doctors and philosophers tried to characterize behavior a number of different ways. One of the earliest medical attempts to describe behavior came from the ancient Egyptians. 3,700 years ago, which is about the time that the Great Pyramids were being created, ancient Egyptian medical doctors were trying to do brain surgery. Now, this must have occurred because the medical doctors recognized the relationship between head injuries and subsequent problems in a person's speech or an inability to move a limb or some other behavioral characteristic. Unfortunately, they took the process of surgery the same way that you would for like a bad kidney or a problem with a liver or being shot. They went in and did a surgical manipulation to try to remove some of the brain, figuring that the brain was actually not functioning properly. But of course, we know today that just going in and scooping out some brain matter would most likely cause many more problems than you actually had originally. And so it doesn't appear that the ancient Egyptians really did much in the way of brain surgery. It's just that they documented their attempts early on, but I have to imagine that without anesthetic or a good understanding of which section of the brain might be malfunctioning after a person received a blow to the head, that there would be a great deal of difficulty from the surgery itself, causing more problems. Beyond those medical attempts, at least in Western civilization, most of the work in the early components of psychology largely came from philosophers. And in terms of Western civilization, we generally refer back to the ancient Greeks in that sense. So people like Socrates and Plato philosophized quite a bit about human behavior. And sometime around 2,500 years ago, there were a lot of the philosophical developments of why people acted the way they did. Now, those philosophical approaches you still see in classwork today if you take a course in the Introduction to Philosophy, but the characteristics of human behavior are done in a very, very broad sense. People like Socrates talked about the nature of human beings and whether or not people were inherently good or inherently bad. They didn't ask the types of questions that you would ask today, like how many digits can you hold in short-term memory, or other types of social psychology questions like why is it that when there's more people around, fewer people are likely to help a person in need. So these very broad philosophical discussions about human behavior largely set the stage for the way future generations would look at psychology. And in fact, the longest period of pre-scientific explanations mainly came from religious philosophers. And there's good reasons for that. Religious philosophers are generally one of a small number of people that are literate in society back over the course of the past 2,000 years or so. And so if a person was going to become a priest or a cleric in any number of different religions, they had to become literate because there were lots of books on philosophy and religion that they had to read to educate themselves about before they could join the order. And then being an individual that was literate, they were then able to use their own thoughts to create modifications of philosophy and then write that down for future generations. And so there's a select view of written material that largely comes from people in religion that focus on human behavior. So again, not general scientific questions about why behavior occurs, but as you might imagine, somebody who's involved in religion is going to take up the torch from people like Socrates and Plato, where they talk about the general nature of human beings and whether or not they're good or evil. And in fact, religious philosophers would have spent more time talking about whether or not people were moral or immoral, and why did they do immoral things, and how could they correct them. So the questions about human behavior were actually very, very general for the longest period of time that we can actually document in written records, is primarily general questions about the philosophical nature of human beings, not specific types of scientific questions that you might ask. Now, let's take a look at a question about that material that we're talking about. What is the name of the process in which a hole is drilled in a person's head? That is, of course, trepanning. Trepanning is the name. Trephinization or trepanning are the names that are related to drilling a hole in a person's head for some sort of medical benefit. Through that lengthy period of philosophy that is both secular and religious, by the time 1600 rolls around, people that had called themselves philosophers or natural philosophers begin developing the scientific method. Now, the scientific method does not develop all in one day, and it's not attributed to one particular individual who was some great genius that pulled all together the components of methodology for science. Rather, the basics of scientific method largely grew out of the development of logic that stemmed from philosophy, and it occurred over the course of possibly 300 to 400 years, really depending upon what you actually want to identify as being a relevant aspect. But it is most certainly aspects of logic and nothing else. We're not talking about technology in this case. There's no physical devices that people are using at that time. It's really a logical sequence of steps to follow that ensures the manner in which you're investigating a topic is going to be correct. So one of the first places that the scientific method gets applied to is in physics. And there's good reason why it actually starts off in physics. It starts in physics largely because what we call today classical physics, like light going through a prism, swinging a pendulum, shooting a cannonball from a cannon, all those things have very consistent and reliable effects. If you shoot a cannonball today, it will go just as far today as it will tomorrow, and it'll go the same distance the day after that. If you swing a pendulum today, it doesn't matter whether it's winter or summer, whether it's evening or daytime, the pendulum will swing the same way all the time. And in fact, that's the thing about classical physics. It has a very rigid structure to it. So when you're just learning about the world, you actually start to see that there is a lot of consistency in these basic aspects that you're looking at. And that fits well with this new basic scientific method, which is not very flexible at that time. In the very beginning, the scientific method was fairly rigid, and it was not understood how well it could expand out into other areas. So it was used in very specific ways for very particular types of scientific experiments. You oftentimes see it applied by people like Sir Isaac Newton, for example, in the beginnings of the time when he started to apply calculus as he developed it back to the physical operation of the world and begin to mix together the data that he collected with the mathematics that he would develop, and that leading clear up to today, there is a very close relationship between physics and mathematics, largely starting from about this time period. After about 75 years of work using the scientific method on classical physics, the physicists begin to realize that they can take the databases that they've generated and start applying them for the betterment of humankind. And that largely begins the development of experimental biology. Now, of course, there were medical doctors long before 1675, and there were people doing work on medicine long before this time period. But this is about the beginning of the point at which a consistent scientific method starts to be applied to the physical world and to the physical aspects of biology so that you could understand medicine better to improve a person's ability to survive a disease or to fix a broken bone or any number of different medical issues. So it's the development of the physical database that really starts being applied toward biology. So what you wind up seeing is biology starts becoming more physical and less spiritual, because prior to this point, it's not clear how any living organism could actually be alive without some sort of spiritual intervention. Right? The ideas that we have today that you probably even take for granted, like the biochemical operations at a cellular level, and the fact that a gene does not have a brain or a mind and it doesn't think, but it just does things based upon chemical processes, is a very foreign idea to people of this time period. And so there's a lot of application of spiritual thinking regarding life and why things operate the way they do. And the development of science from around 1600 and the knowledge base that it builds starts chipping away at that spiritual idea, and it starts focusing your attention much more on the physical operations that control medicine or health, as opposed to any kind of spiritual aspect. From 1675, we're going to hop ahead to about the 1700s. The reason why we're jumping ahead to this point is because we are ultimately headed toward our understanding of psychology. And so one of the physical developments that occurred along this way that is very important for the field of psychology is the development of electricity, and even more so, the recognition that electricity is inside of your body. During the mid-1700s, something called a Leyden jar was developed. A Leyden jar is essentially an early form of a battery. It's essentially a capacitor. A capacitor is basically a battery that discharges all of its electricity in one shot. And that's what these Leyden jars were. But it was the first time anybody actually had the capacity to store electricity in a glass bottle. And so it became a rather remarkable piece of technology at that time. And because there were many fewer scientists, many of them would dabble in different areas of study from what they were trained in. And so people were getting these Leyden jars and they would apply it to either physics or biology or whatever area that they were actually working on. During this time, an individual named Luigi Galvani was doing anatomical work on frogs with his assistant. And during this time period, they had a Leyden jar, and they were using the Leyden jar to electrocute the frog after it was dead. And either it's not clear from the historical record whether this was done on purpose or by accident, but the tips of the Leyden jar were applied to a frog's leg. And when the electricity ran through the leg, the frog's leg moved. So that is, the frog is dead, its leg was removed from its body, but when electricity was run through the leg would actually jerk. And that became kind of the theoretical basis to why there was a concept of electricity inside your body. Prior to that point, the older theoretical idea for how nerves operated your body came from the idea that there was a high pressure fluid that ran through your nerves. So anatomically, if you take a look at the brain, there are actually ventricles. These are essentially internal pools of cerebrospinal fluid. And before the time of microscopes, it was believed that your brain essentially functioned like a large muscle that would squeeze the fluid from the brain through your nerves, and that hydraulic system would be the basis to which your body would actually move. This application of electricity to a disembodied frog's leg became the second, a more prevalent theory over time, indicating that you could run electricity through a nerve, and that was the basis by which things moved. This would lead to a variety of different types of experiments that were really rather remarkable that we're going to talk about in a moment. But before we do, let's take a look at this question. How long after the beginning of science were the first Leyden jars invented? 145 years. That's correct. Because science begins at about 1600, and it was about 1745 that the first Leyden jars were created. So after those Leyden jars were created, what you wind up seeing is an application of electricity to a wide range of medical interventions. In fact, the application of electricity as a medical intervention was so common that people in the general public were typically aware of it. And it was not just the application of electricity, but it was some of the odd experiments that were being conducted that also made people take notice. So, for example, in the late 1700s, usually identified sometime around the 1790s, a fellow named Christian Kratzenstein used electricity to electrocute the legs of paralyzed patients. Because, from a medical standpoint, electricity seemed to be a stimulating event, right? If you electrocute yourself, it would be kind of characterized as a stimulating aspect. Now, if you think of electricity as a stimulating aspect and then take a look at a person who's paralyzed and stuck in a wheelchair, you might think that the stimulation from the electricity might flush out a clog in the person's nerve, thereby giving them the opportunity to walk again. So the medical view of paralysis back in the 1790s was the idea that a nerve had become crushed and it was not allowing electricity to flow through. So as a result, medical doctors took these larger versions of Leyden jars and they would electrocute the patients in the hope of flushing their nerves out in the same way that Drano cleans out a pipe in your kitchen sink. And so Kratzenstein would go off into the woods and he would find dead animals, oftentimes dead birds, bring them back to his laboratory and electrocute them to try to bring them back to life. Which of course does not actually work, but if the body of the bird is relatively new, by electrocuting it, it would still start to move, and that would always give him a reason to believe that, if he used enough electricity or found a fresher animal, that it might actually just pop back to life. Some of the other applications from these Leyden jars are made by a fellow named Giovanni Aldini, who was Galvani's nephew. Now, Aldini is generally known as a quack doctor today because he took the use of Leyden jars to an extreme in his medical practice. So no matter what medical problem a person had, Aldini would electrocute that individual for the betterment of them. So if you had a headache, he would electrocute your head. If your knees hurt, he would electrocute your knees. If you had stomach pain, he would electrocute your stomach. It was just kind of a one treatment doctor. And under these circumstances, what he would do to get electricity at a higher power than he could with his Leyden jars is he would go down to the docks when fishing boats would come in, and if anybody had caught electric eels, he would buy the electric eels from the fishermen, stick them in buckets, and he would have an individual stand in the bucket with the electric eel, agitate the eels, and make them electrocute the individual. And then you would have to pay him for treatment like this. And that attempt was, from Aldini's standpoint, a way to get much more electricity into the person's body to flush out the nerves to improve their medical health. One of the other applications that Aldini took, which really kind of made him stand out historically, was to extend on what Kratzenstein did. Instead of just taking dead birds out of the woods, Aldini decided that he would try to resuscitate executed criminals. So, if an individual was found guilty and hung by the neck until dead, he would get permission from the city council ahead of time to take the fresh corpse and electrocute it with a whole series of Leyden jars to try to bring the person back to life. That is, to prove that electricity was the basis of how a person stayed alive, that he would try to electrocute these individuals and bring them back to life. And one of the most dramatic instances of this, I believe, occurred in about 1811, in which Aldini electrocuted the fresh corpse of an executed criminal in which case the criminal, being electrocuted so much, actually sat up on the gurney in front of the townsfolk. And that caused chaos because it appeared as though he actually brought this person back to life, whereas what's really happening is just the body still being freshly dead still has some of the intact nerves in it, so that by electrocuting the individual's corpse, you'll cause the nerves to function and the muscles to still seize up. So if their legs are strapped down and you electrocute their torso sufficiently, they'll actually sit up. But people thought that the executed criminal was actually coming back to life, and so there were reports of people passing out and vomiting. A few heart attacks had occurred. The couple people actually died, apparently from stress afterward. Beyond this point, one of the applications that you see with electricity during this time period come from further applications in medicine, which will be laid out right here.
Doors have been opening for Emma since she was a hooker aged 14, from which she graduates to be mistress of various aristocrats. She hits the big time around 1780, pouring drinks for the well-heeled suckers who are flocking into London's latest health and beauty salon with a difference, where they charge you, in more senses than one, with electric shocks. Dr. James Graham claims his current treatment will generate a galvanizing effect on anybody who has a spark of life in them and wants to be a real live wire. And if you think that sentence was dreadful, you should read Graham's original sales pitch. But where Graham really scores is with his electrico-magnetico-celestial bed, where, if you can't have children, a few high-voltage sessions with the good doctor, and from then on, all your troubles will be little ones. Now, this may all look like indictable offences to you, but you've got to remember that back then, this is high-tech amazement. I mean, who knows? This quack is a fully paid-up member of the respectable professional classes, a friend of Benjamin Franklin and various dukes and duchesses. And of course, he's studied at the best medical school in Britain, Edinburgh, where he is taught by a fellow with a drinking problem.
So we see in the previous video, the use of electricity was used for a very wide range of medical applications. In this particular case, reproduction. But you also saw in the video that it was used for treating headaches when they shocked the man's head. And in fact, as we kind of talked about with Aldini, he used electricity as a treatment for essentially everything. Now, the use of electricity is going to expand into the 19th century, that is the 1800s, in a variety of different ways, but it's not going to be the only development that occurs. In fact, a variety of other developments in the control of electricity from the field of physics, as well as advancements in biology, will lead to some of the developing components that ultimately make psychology start in 1879, as you see down here on the bottom of the slide. To start with, there are a number of dates that you see on this particular slide, from the 1820s down to 1879, and 3 of them have stars next to them. The starred dates are dates that you're going to see all semester long. We will continually refer back to what had happened in the 1820s, 1859, and 1879 as setting events for the development of different areas of psychology. The other dates are, of course, relevant, but we won't refer back to them as much, and that's why those stars are there. In the 1820s, what had happened is a fellow named Ernst Weber, who was a biologist and had 2 brothers who were both physicists, all of them academics, would work on developing scales of measurement in their spare time. So what they did was, this being 220 years after the development of physics, and physicists feeling pretty good about themselves, started to realize that there were some scales of measurement that they still did not have. For example, how do you measure sound in the 1820s? Well, if I were to ask you that question today, the answer would be simple. You could just buy an electronic device that would measure the volume and particular pitches and so forth that are all related to sound. But how do you do that when there's no electronics? In the 1820s, light bulbs don't even exist. And in fact, there's only rudimentary control of electricity itself. Well, there's one device that will measure sound for you, or other types of things like light, brightness, for example, which is also a non-existent scale in the field of physics at the time. And that one device that will measure sound and brightness is a human being. You can play sounds or shine light into an individual's eye, and they can give you their impression of how bright it is. Now, when work like this starts to take place, there is a reasonably good experimental setup to establish clear relationships between the external source of energy and an individual's perceptual experience of it. As a result, a lot of good data is collected, and it starts to establish itself into what's ultimately called Weber's law. Weber's law is actually a recognition of the change in perception of an external stimulus being a constant percentage of the amount of stimulation you're exposed to. That rule is something we're going to work with more in the sensation and perception chapter. For now, it's an underlying aspect that reflects the fact that human perceptual experiences follow consistent biological rules. In 1825, based upon the rudimentary control of electricity, small electrodes were able to be developed in the laboratory, and primarily in France, work on brain mapping was being done with dogs. Dogs were used because they were sufficiently large enough that if you removed their skull, there was a sizable portion of brain matter available that you could electrocute in a systematic fashion across the outer surface of the brain with an anesthetized dog, so that you could see if you stimulated one particular area of the brain as opposed to another, whether or not there would be any automatic physical reaction in the dog. As we'll see in the next chapter, there's an area called the primary motor cortex in the brain, and by stimulating that area, even in an anesthetized individual, you will automatically cause their hand or their arm or their leg to move. Consequently, these early biologists doing brain mapping experiments started to show that the brain, even though you couldn't tell what was where by looking at it, you could actually detect some of its circuitry by stimulating certain areas of the brain and establishing a map from its outer surface. By 1852, it was clear that nerve conduction speed inside your body runs at about 90 feet per second. Perceptually, originally, biologists seemed to think that nerve speed inside your body probably travels at the speed of light. And that's largely because when you look at yourself touch something, the point at which you seem to perceive your finger touching an object seems to be as essentially the same point in time that you perceive that object. There's no delay between them. And because you're talking about electricity, and electricity was at this point in time physically somewhat tied to light, the assumption was nerve conduction speed traveled at the speed of light. But of course it doesn't. It actually travels much, much more slowly. So to do work that established the speed of nerve conduction, a fella named Hermann von Helmholtz started to conduct experiments with frogs and with humans to determine the rate of electrical movement through the body. And upon conducting those experiments, found that electricity inside your body moves at about 90 feet per second. To give you an idea, if you had a giant human being who was as tall as a football field, right? So if they laid down, their head was in one end zone and their feet were in the other end zone, and you tickled the person's foot, it would take about 3 seconds for the electrical signal to travel from their foot to their head, and another 3 seconds back before they would jerk their foot because you had tickled them. In 1859, the second most significant aspect of the 19th century occurred, and that was the development of the theory of evolution. As we'll see in the neuroscience chapter, the role of evolution is very relevant for psychology, largely because it places an organizing structure upon the development of brains and the overall organizational structure of a nervous system across a wide variety of animals. And so as a result, you wind up seeing a lot of similarity between creatures that you might have missed had you not actually been specifically looking for commonalities in brain structure given the theory of evolution. During the 1860s, reaction time studies started to be developed, and reaction time studies are still used today because they are very effective ways to determine the pathway of information through your brain. What reaction time studies are types of experiments which evaluate the role of decision making and perceptual experiences for a subject, and using each of those points to determine whether or not they add to or subtract from the length of time it takes a person to make an answer. So if I were to show you a red light and I say, press the space bar on the computer as soon as you see the red light, that would be a simple reaction time. Now, if I said, I'm going to show you a red light or a blue light, and only press the space bar if it's the red light but never the blue light, each time a light turned on, you have to make a decision before you respond. And as you might imagine, in a scenario where you have to look at the light and then decide whether to respond, actually always adds a little bit of time extra into the point at which you actually respond, relative to a scenario where there's only one light and you just simply respond to any light that comes on. In a whole series of experiments that you can do in a much more sophisticated fashion, you can actually create theoretical brain circuitry inside of a human being back in the 1860s to estimate what pathway information actually takes, and use this kind of as a way to gauge the internal circuitry of the brain. And as I've mentioned, this type of process actually works very well, and so it's still used today. Occasionally you hear about experiments like this in popular psychology journals, where you'll hear about how people have to press a bar as soon as they get some information or make a decision about it, and then the length of time it takes them to respond is actually part of the primary source of data that's being evaluated. After the 1860s, we finally get to the point at which the field of psychology is developed in 1879. And because we're here delving into this history, I'm going to go a little bit into what actually happened just before 1879. Vilhelm Vaunt was a medical student. And as a medical student, he had to take night shifts at a hospital. And while he was there, very, very sleepy, he almost poisoned one of his patients by accident. And as a result, he decided to get out of medicine because he didn't want to accidentally do this kind of thing again. But he finished his education and essentially got what you would refer to today as a PhD in biology, as opposed to a medical degree. Now, with his doctorate in biology, Wundt sets out to get a job once he's graduated, but he was having difficulty finding work. Now, things are different here in the late 1800s than they are now in the 21st century. In the late 1800s, if you had a PhD in biology, you could essentially take a job as a physicist or as a chemist or as a biologist or even possibly as a mathematician, depending upon the amount of math you had. And the reason is the databases for all these areas were so much smaller back then that if you had gotten a PhD in one field of science, you knew so much of the other areas as well that you could largely switch fields. And this is about the very last point in time in history where you could actually flip-flop. And there are a number of instances of people just getting degrees in physics and then working as biologists, or biologists going off and working as medical doctors and so forth. But you don't see it much beyond this point. In Wundt's case, as he had difficulty finding work, he eventually took a position in the philosophy department at the University of Leipzig. Now, at the university, in the philosophy department, Wundt was expected to study philosophy that had been around since the beginning of Western civilization. So things like Aristotle and Socrates and so forth. But Wundt has this background in science and biology. So he decides that he does not want to do traditional philosophical work, but instead he's going to take his background in science and apply it to understanding why human beings think the way they do. So rather than being purely philosophical about it, he wants to set up experiments to evaluate why people act the way they do and why they think the things that they do. And that largely becomes the very first psychology laboratory. It is the mixture of scientific biology with philosophy, because a man with a PhD in biology who wound up with a job in a philosophy department simply didn't want to do traditional philosophy. He pulled together all his available resources at that time and created something completely new: the scientific study of psychology. And that's where the first psychology laboratory came from. So now that we've gotten to the point where the first psychology laboratory is set up, and we understand why psychology started the way it did, because of a biologist in a philosophy department started to do new type of work, we are largely finished with the historical components of psychology, and we're going to move on to some of the basic definitions of understanding how psychology works. Now, if you ask people to define psychology, many people will tell you that psychology is defined by the scientific study of thoughts and feelings. And that seems fine for most people, except there's a problem with that type of definition. The problem with that definition is the fact that thoughts cannot be measured directly. And one of the things about a scientific process is that all the sources of data must be publicly observable and objective. Those two characteristics must always be present if you're conducting a scientific investigation. Now, publicly observable is very obvious. That means that when the data are collected, it's something that anybody can see. You can never say, I collect data in my laboratory, but nobody's allowed to come by and see the data and then talk about the grand ideas that come from your data. You can never hide things in a scientific process. It's a very democratizing process. Everybody has to see the same thing so that everybody's on board with what's actually happening. The second process, objective, actually means that the source of data is all being measured in the exact same way by everybody who talks about it. So objectivity, or the data being objective, simply means that everybody's measuring it the same way. So if you were to measure the length of an individual, you don't want one person using one scale of measurement like the English imperial system and then somebody else using the metric system, and that would of course lead to confusion. Of course, you can create scales to switch over from the English imperial over to the metric system if you want, but it causes confusion when you have multiple systems. So you want an objective measure, everybody measuring things the same way. Now let's take a look at thoughts. Are thoughts publicly observable? No, they're not, because thoughts presumably occur inside your head. And if a person sits perfectly still, doesn't move, they can have the greatest, most grand thoughts in the entire history of humankind, and you would never know it because they're simply not doing anything that you can actually measure. As a result, thoughts and feelings as well, which fall into the same boat, are not directly measurable. So you would actually have to call them immeasurable. They cannot be directly recorded. And as a result, you cannot use thoughts or feelings as the source of data in a psychology experiment. Now, if you can't use thoughts or feelings, can't you use other kinds of things that are related to it, like verbal reports, brain scans, or electrical activity off somebody's head? Well, you can use those things, but they don't replace the thoughts and feelings themselves, because verbal reports, what a person says about their thoughts, is not the thought itself. It is what the person says about the thoughts. Now, you might think that's splitting hairs, but it turns out that is a very big difference. And in fact, later in the semester, we will see that what a person thinks and oftentimes what they say about their thinking can sometimes be completely at odds, entirely different from each other, and the person will not even know that they're doing it. And you can actually show this. So it's very important to recognize the difference between what a person says and when they're trying to reflect their thoughts and the thoughts themselves. And when you take a look at brain scans and measuring electrical activity or hormonal activity from an individual, those basic physiological responses might seem like they could be connected to thoughts and feelings, and they can to some degree, but they are not the thoughts or feelings themselves. And again, they only exist as secondary measures of the thoughts and feelings themselves. So if you ask a person to talk about their thoughts and then they speak or write it down, that is considered a verbal report. Verbal report is any communicative process. It doesn't necessarily mean speaking necessarily. It's all types of human language that are involved. So verbal reports are always a secondary measure of a thought or a feeling, as are brain scans and electrical activity. Now, it's absolutely true, by scanning a person's brain, reading the type of electrical activity off of their brain, you can get an idea of where things occur in the brain and to some degree the amount of activity that it involves. And you can use that for other things. But electrical activity off the brain is only a direct measure of electrical activity off the brain. A brain scan is only a direct measure of brain scan activity, whether it's measuring magnetic impulses or electricity or some other thing like radiation. like PET scans use. But those are not direct measures of the thoughts or the feelings themselves. So if you don't have direct measures of thoughts or feelings in this case, what are you actually left with? Well, when you take a look at this slide, if you cannot directly measure thoughts or feelings, you are left with behavior. Any overt measure of activity is a sufficient direct measure to be used in a psychology experiment. And in fact, given that we have electronic equipment today, one of the simplest ways to say this is anything that can be audio taped or videotaped is an appropriate measure for a psychology experiment. Because if you can audio tape it, then you could directly measure it. If you can videotape it, then you can directly measure it. There's no guessing about what a person's thinking or feeling. You are directly measuring what they're actually doing. So the source of overt behavior is always publicly observable so that you can record it here and you could send it to your Chinese colleagues on the other side of the globe and they could evaluate exactly what you're looking at. And it is an objective measure, or it lends itself to being an objective measure so that everybody can measure the activity in exactly the same way. So when you're working with behavior, you are squarely in the realm of science. If you try to keep pushing estimates of thoughts and feelings, then you start skirting science and you start getting into pseudoscientific activity. Now let's try to apply this idea in this particular question. Which of the following would not be useful as a measure of behavior? And the answer there is D, thinking quietly. All of the other answers there are things that could be audio taped or videotaped. They are all publicly observable, and therefore they all lend themselves to being objective measures, measured in exactly the same way as everybody else does. So running is a simple one. Everybody can see that. You can videotape somebody running, and any scientist anywhere in the globe can look at it a week later, a month, or a year later, and it will be exactly the same data. The same thing with hand gestures, which are overt behavior. The writing you leave behind in texts or in cursive or in any other source of communicative process like that, you leave behind a record, and therefore it's an objective measure and publicly observable. As well as eating, which of course can be videotaped. Thinking quietly does not meet the publicly observable objective requirement of a scientific process. A person who sits in a chair and is completely immobile can have the grandest thoughts, and you would never know it unless they can communicate those thoughts to you. And once they communicate those thoughts to you, they then are behaving. And that behavior can then be recorded by a videotape or an audio tape, and then you have a publicly observable objective measure of what they were doing. But you do not have that until they finally move. In fact, the field of psychology, in particular the field of clinical psychology, has a thing called the dead man's test. If you as a clinician want your patient to stop doing something, it is completely wrong to try to get them to stop doing a behavior as opposed to doing some other behavior. And why this difference is important is because if, for example, you have a 6-year-old who keeps misbehaving and the parent tries to get that child to stop misbehaving by telling them to sit down and shut up, the only thing that's going to happen is that child will sit still, but they won't learn an appropriate alternative behavior. And sitting quietly and not doing anything is actually not to the child's advantage. What you would rather have the child do is something useful and creative and intellectual, whether they're playing frisbee on the front lawn or drawing or doing something else. There are lots and lots of patterns of behavior that a child can do that are perfectly appropriate, as opposed to remaining quiet and sitting still all day long.